In the figure, four long straight wires are perpendicular to the base and their cross sections from a square of edge length A is equal to 17.5 centimeter. Each wire carries 7.5 ampere and the currents are out of the phase in the wires 1 and 4 and into the phase in wires 2 and 3. In unit vector notation, what is the net magnetic force per meter of wire length on wire 4? Given the data, square of each length A is equal to 17.5 centimeter. The centimeters is converted into the meters. A is equal to 1 centimeter is equal to 10 to the power of minus 2 meters. So A is equal to 0.175 meter. The current carrying the each wire is I is equal to 7.5 amperes. Draw the figure. Consider the square. Consider the square. This is a square and current carrying the each wire is I. This is the wire 1. This is the wire 2. This is the wire 3. This is the wire 4. Let us consider this is the square. Each side length is the A. This is the square. Each side length is the A and the current carrying the corners of the square. The current carrying the corners of the square. So the current in the each wire is the I. So current in the wire 1 is the I1. Current in the wire 2 is the I2. Current in the wire 3 is the I3. Current in the wire 4 is the I4. So the wire 1 and wire 4, the current direction is out of the phase. So the direction of the current in the wire 1 is out of the phase and wire 4 is the out of the phase. And the current through the wire 2 and 3 is the into the phase. So the current through the wire 2 is the into the phase and the current through the wire 3 is the into the phase. So let us consider the distance between the let us consider the magnetic force on the wire 4 due to wire 1 and wire 2 and wire 3. So the distance between the wire 1 and wire 4 is the A. The distance between the wire 2 and wire 4 is the this is the distance between the wire 2 and wire 4. This is the distance between the wire 2 and wire 4 is the R. And the angle between the wire 2 and wire 4 from the horizontal is the alpha. This is the alpha. So the distance between the wire 2 and wire 4 is R. R is equal to root over A square plus A square. A square plus A square. So R is equal to root over A square plus A square is equal to 2A square whole root. So root 2 into A. The angle between the wire 2 and wire 4 from the horizontal is alpha. Alpha is equal to tan inverse root over tan inverse A by A. Side length by side length. So opposite length by adjacent length. Tan A by A. Alpha is equal to tan A by A is equal to tan inverse 1. Tan inverse 1 is equal to 45 degrees. So tan inverse 1 is equal to 45 degrees. Let us consider the magnetic force, the direction of the magnetic force due to wires. So consider wire 1 and wire 4. Both are the current carrying the same direction. So the current carrying the wires in the same direction, they are attract to each other. So the magnetic force on the wire 4 due to wire 1 is direction is the upwards because both are the same current carrying the same direction. So they are attract to each other. So the wire 1 attract to the wire 4. So the direction of the magnetic force is upwards. So the current carrying the magnetic force is F14. The force acting on the wire 1 on wire 4 is the F14. Direction is upwards. And the direction of the magnetic force due to wire 2 on wire 4. This is the both are the opposite direction. So wire 2 is the into the phase and wire 4 is the out of the phase. So both current carrying the opposite directions. So the current carrying the both wires are opposite. They are repelled to each other. So the magnetic force is away from it. So the magnetic force on wire 4 due to wire 2 is the towards the direction. This direction is the downward left. So the magnetic force on the wire 2 F24 towards the downward left. The magnetic force on the wire 4 due to wire 3 is both are the opposite directions. The current carrying the two wires are opposite directions, so they are repelled to each other. So the direction of the magnetic force towards the leftward. So the magnetic force on the wire 4 due to wire 3 is the F34. The direction towards the leftward because both are the opposite directions, so they are repelled to each other. Let us consider the net magnetic force on the wire 4 due to wire 1, wire 2 and wire 3. So the net force acting on the wire 4 is the F bar. F bar is equal to vector sum of the magnetic force due to wire 1, wire 2 and wire 4. So F bar is equal to the magnetic force on the wire 4 due to wire 1. So F14 plus the magnetic force on the wire 4 due to wire 2 is the F24 plus the magnetic force on the wire 4 is the on due to wire 3 is the F34. So this is the magnetic force. So the net magnetic force F bar is equal to the magnetic force on the wire 1. The magnetic force on the wire 4 due to wire 1 is the F14. F14 is the mu naught into I1 I4 L by 2 pi A. The side length is the A. The direction along the upward, so positive Y direction, so taken the J bar. And the magnetic force due to the wire 2 on wire 4, that is the F24. F24 is the direction along the downward left, so taken the negative sign, negative. The value is mu naught I2 I4 L by 2 pi. The distance is the R, 2 pi R into cos alpha I bar plus sin alpha J bar. And the magnetic force due to wire 3 and wire 4 is F34, where F34 is the direction along the leftward, so negative x direction, so negative. The value is the mu naught I3 I4 L by 2 pi. The distance is the A along the I bar. So from this equation, the current carrying the each wire is the I. So consider F bar is equal to mu naught into I1 I2 means I square L by 2 pi A, the direction along the J bar, minus mu naught I2 I4 means mu naught into I square L by 2 pi R. R is the root 2 into A. So root 2 into A into cos alpha I bar plus sin alpha J bar minus mu naught into I3 I4. I3 I4 means I square L by 2 pi A, the direction along the I bar, So from this equation, common the points mu naught I square L by 2 pi a. So F bar is equal to mu naught I square L by 2 pi a. So let us consider first of all I components. So minus mu naught I square L by 2 pi a, mu naught I square L by common point. So minus into 1 plus, consider the cos alpha by root 2. So cos alpha by root 2 along the I bar, I direction, and consider the mu naught I square L by 2 pi a in plus j bar. So plus 1 minus sin alpha by root 2 along the j direction, along the j direction. This is the magnetic force on the wire 4 due to wire 1, wire 2, wire 3. So let us consider the magnetic force per unit length is small f bar. This is the magnetic force per unit length. Small f bar is equal to force per the magnetic force per unit length F bar by L. So this is the magnetic force per unit length. Small f bar is equal to F bar by L. Small f is equal to mu naught I square by 2 pi a into minus of 1 plus cos alpha by root 2 I bar plus 1 minus sin alpha by root 2 j bar. So substituting the values in this equation, the magnetic force per unit length, the vector notation F bar is equal to mu naught is the constant. The constant value is the 4 pi into 10 to the power of minus 7 T m by a into the value of the I is the 7.5. So 7.5 amperes whole square whole by 2 pi into value of the A is the 0.175 meters into minus 1 plus cos alpha is the 45 degrees, cos 45 by root 2 I bar plus 1 minus sin 45. Sin alpha means sin 45 by root 2 j bar. Simplifying the equation, multiplying the equation, F bar is equal to the magnetic force per unit length F bar is equal to cos 45 by root 2 is equal to 0.5. 0.5 plus 1 is equal to 1.5. 1.5 into minus 1 minus 1.5 into this value is minus of 9.642 into 10 to the power of minus 5 I bar, and sin 45 by root 2 is the 0.5. 1 minus 0.5 is equal to 0.5. 0.5 into this value is the plus 3.214 into 10 to the power of minus 5 along the direction j bar. So the unit is Newton per meter. The vector notation of the magnetic force on the wire 4 is F bar is equal to minus 9.642 into 10 to the power of minus 5 I bar plus 3.214 into 10 to the power of minus 5 J bar Newton per meter. This is the net force acting on the wire 4.